Okay, so we are going to look at chemical bonds, and one of the things we're going to do is classify them in two main categories, intramolecular and intermolecular. So when you put elements or atoms together, then you make molecules, you can make compounds. Sometimes you'll get transition metals that come together. And usually we often put things together to create different properties. So for example, maybe one of your parents or guardians, grandparents, maybe they wanted to preserve your little shoes from when you were a baby, so they cover them in brass or bronze, which is an alloy. It's a mixture of metals, but it makes the metal a little bit tougher, so it'll last longer, so they can keep it forever and remember your tiny little shoes, that kind of thing. And if you think about it in a purely scientific way, if elements didn't want to join up, then all we would have is the 92 elements that are natural, not synthetic or man-made. And so that would really limit the diversity of molecules and compounds and diversity of life that's found on Earth. So we can put things together, and even the difference in one atom makes a very new substance. So water is H2O. We need water for life. We drink water. We feed water to our plants. And then when you have H2O2, one more oxygen, that's hydrogen peroxide. You put that on your cuts and it bubbles and it kills bacteria. So obviously you wouldn't drink that, okay? So very different properties, even with one more atom, which creates a greater diversity in what can happen on Earth. So we have different classifications of bonds. Whether you call them bonds or forces, it doesn't really matter. So we're going to the most broad category, intramolecular and intermolecular. If you are into, again, tricks or ways to remember this has an A. Atom starts with A. That's the best I got. So molecules are specifically like molecular compounds where they have covalent bonds. We sort of throw the word molecule around to mean, any kind of compound, which really it isn't, okay? So you're going to see when we talk about covalent bonds or sharing of electrons, then we can get some very strange things happening. So you think about if you have a sibling or somebody close to you, and you have a cookie and you break it in half, and you have to share. Are you going to share the big piece? Are you going to share the little piece? Is it going to be equal? So there's lots of crazy things that can happen with sharing. Whereas when you have metals, so whether it's metallic or ionic with a metal and a non-metal, that's very ordered. Plus, minus, cation, anion, cation, anion, cation, anion. Very, very ordered pattern. So not a lot of weird things can happen. So intramolecular forces, that when you have ionic and metallic, that's sort of the end. Whereas covalent, you can get some strange forces happening. So we're going to talk a lot in grade 11 about ionic and covalent, and then we're going to introduce intermolecular, and then in grade 12, we're going to focus more on intermolecular, okay? So it's kind of the next step. So intramolecular forces, because they are between atoms, they are very strong. There's sort of a gradient in the strength of intermolecular. but it's still weaker than intra. So we'll just keep it like that. So intramolecular forces or bonds are formed or broken between when you do a chemical reaction. Whereas intermolecular forces or bonds are manipulated during physical changes like freezing, melting, boiling, that kind of thing. So in grade 12, we're going to talk more about the actual amount of energy required for these changes. Again, sort of moving towards a more quantitative idea about chemistry. Okay, so there are 5 major types. So the first 3 are intramolecular, ionic, covalent, and metallic. I think you have to, all I wrote down was the name, right? Yes. Pick a different color and highlight the types of atoms. So we're going to talk about ionic and covalent the most. And again, you would have talked about those in grade 10. Ionic bonds occurring between a metal and a non-metal. Electrons are transferred. Whereas in a covalent bond, they are shared. So that's going to influence the kind of Lewis structure we draw. Ionic compounds where the electrons are transferred, the nonmetal gains the electrons and does not give them back to the metal, whereas in covalent bonds, because you have two nonmetals, they are said to share the electrons. They spend some time around the one atom's nucleus and some time around the other atom's nucleus. And then the difference between that sharing, is it equal or unequal? That's where you need your periodic table can help you figure that out, okay? And actually you might notice or start to notice patterns. And then next year when you get to grade 12 or even biology and we look at molecules in our body and things like that, you'll start to notice a pattern in whether something is what we call polar or non-polar, whether it dissolves in water or not, those kinds of things. Transition metals, we will talk a little bit about their unique electronic structure. So they're one of the reasons they have more than one charge. So if you remember, you had to do Roman numerals, that kind of thing last year. So they have such a unique electronic structure. So we call it a region of free electrons, not even the orbits like Bohr said. So their metal atoms can join together to make an alloy. So really strange things can happen. They can conduct electricity in a solid state, which we make use of. Copper wiring is the most common in homes, that kind of thing. And then the intermolecular forces are hydrogen and van der Waals forces. And like I said, we'll sort of scratch the surface in grade 11 and then really focus on these in grade 12. Okay. Oh, did we talk it? No. So hydrogen bonding, again, is one of those things that we need for life. And there's plenty of natural phenomena that exist because of the presence of hydrogen bonding. So we're actually going to do a whole unit on water and solutions. So we'll talk more about specifically how hydrogen bonds affect water. Again, if you're into biology, you will talk about the hydrogen bonds in DNA molecules, that kind of thing. And then van der Waals forces are useful to help explain the difference between molecules like, say, methane, which is natural gas, the molecule that comes out of our taps as a gas. It has one carbon. Why does the gasoline you pump in your car, which is 8 or 10, why is it a liquid and not a gas? So those forces, or the van der Waals forces, can help explain what's happening there. Okay, so I think you just need to fill in the box. So the first important idea about ionic bonds, they are formed between a metal and a nonmetal. We'll worry about, the crisscross rule and stuff like that. That's the very beginning of Unit 2. But in grade 10, that's really, you spend lots of time, trying to figure out what the formula is for a compound or write the name. When you have an ionic bond, the metal could be a transition metal. It doesn't matter. It could be alkali earth, transition metal, one of the other metals. It has to be a metal and a nonmetal, or even you could even think of it like a cation and an anion. Something has to be positive and something has to be negative. So when it talks about the electrostatic force of attraction, that means that you have an opposite charge that are attracted to each other. So the plus and the minus are attracted. So the next few slides we kind of already talked about. So if you have an ion, so say we have sodium. So sodium has 11 protons, 12 neutrons. Okay, then if it's an atom, 11 electrons. And then when it becomes its ion, Na plus, and again, you can write the 1 or not. It loses the outer electron. Now it only has 10. So it has the same number of electrons as neon. So it always has to be a noble gas that it's isoelectronic with, or the same number of electrons. So then cations are positive, anions are negative. If I know there's no little periodic table there, but if it helps you on your periodic table to write up here, probably your grade 10 teacher encouraged you to do that. We're going to skip the middle. We're not worried about carbon, right? It's not going to be, does it lose, does it gain? That's not a thing. And then, of course, the noble gases don't react. So if you want to do that on your periodic table, you can, but you don't have to. Okay, so the big thing with ionic bonding is that the reason you get cations and anions is because of the transfer of electrons, not sharing. So that's like the second difference. So a metal reacts with a nonmetal and it transfers the electrons. The metal gives up electrons to the nonmetal. It does not get them back. And they're attracted to each other pretty strongly. So usually ionic compounds are very hard, brittle solids, like table salt. Okay, so then this is just an example, lithium and fluorine. Lithium's an alkali metal, um, fluorine's a halogen, so they both have a charge of 1. That's the simplest kind of ionic compound. So lithium loses 1 electron to become isoelectronic with helium. Fluorine gains that electron to become isoelectronic with neon. Then they come together, the positive and the negative, and you get lithium fluoride, which is what we're going to do next. Okay? Not next, next unit, sorry. So another thing that's important is the properties of ionic compounds. So they form what's called solid ionic crystals. Now, because we should not use the word molecule unless it's nonmetals, then we often call these salts. Your textbook loves to call them formula units. People often just call them ionic compounds too, that's fine. But you should not say molecules. So molecules are for covalent bonds, molecular compounds, okay? Ionic compounds are unique in that they will dissociate in water to make what we call an aqueous solution. So aqueous solutions are important in for a lot of applications in chemistry. So when you guys did labs like you would have done the conservation of mass where you had a flask and a little tube and you mixed them together. That was not melted sodium hydroxide. It wasn't a liquid. That was an aqueous solution. Acids, so the reason we have water first and then put acids in it is because acids are water loving. I've never actually seen a solid acid or worked with a solid acid. They're always dissolved in water, because they make aqueous solutions so readily. So one of the things we're going to do later as well is look at what solids don't dissolve in water and what solids do dissolve in water. So the formation of a precipitate is a big deal. In grade 9, you would have learned about signs of chemical change, and making a solid was one of them. So the presence of ions in water is a big deal. And here, in just for physical properties, it's a big deal because aqueous solutions will make what we call electrolytes. And electrolytes is another word. Sometimes people will call like Powerade or Gatorade an electrolyte, which is fine. Yes, it has ions in it. It probably will conduct electricity. But they're trying to say if you sweat, then you lose your ions. You need to replace them. You need to replace your electrolytes. Really, the definition of electrolyte is a solution that conducts electricity. This also makes tap water very dangerous. Tap water is full of ions, sometimes on purpose. Often in developed countries, we put fluorine in our water to help with our teeth. And depending on where you live. So we live in an area that has, sometimes you might hear somebody say, oh, the water is very hard. Or if you have a well, if you live in the country that you have hard water, and that seems ridiculous. How can water be hard? It's because it's got ions in it. So in this area, usually calcium and magnesium, and that can influence the taste. It can influence how well it washes. Like you might hear whoever does your laundry complain that your white shirts don't get very white. Especially Paris has really hard water too. So that kind of thing. It doesn't mean hard. It means that it has ions in it. So if you have a salt, if you ever have to change the softener salt, what you're doing is a chemical reaction. You are getting the water passes through there. It reacts with the salt to make a precipitate, takes the ions out of the water, so then the water has less ions in it. And things like if you're a tea drinker, if you've ever looked at the element, like if you have a plug-in one and it's got corrosion, maybe you add vinegar to it to clean off, or coffee maker to clean off the ions, that kind of thing. So in this area we have pretty hard water, which means also that electricity and tap water do not mix. Okay, so it can be very dangerous. That's why we use distilled water in our experiments, because or sometimes you might hear of deionized water. We are removing the contaminants in order to make sure our water is pure. Later on, when we do acids and bases, we also want a purely neutral solution, pH of 7. We don't want it to be acidic or basic. Um, Sometimes you might hear people talk about that as well. So why do aqueous solutions conduct, but solid ionic compounds don't? So another reason why aqueous solutions are important is for displacement, like that switching reaction. Your grade 10 teacher might have, talked about girls dancing, or a girl and a boy, and then the girls switch. They love that analogy. So in order for conductivity to occur, in order for displacement reactions to occur, you need to have the ions broken apart. If you have a solid compound that's like table salt, that's very brittle, you could smash it and it would just crack. Very, very, very unreactive. Once you put it in water, the ions are dissociated, or we call them free. So in a reaction, they're free to switch. When you're talking about current, then you need a path for the electricity to flow. So that's why we use wires, because it provides the path. So somebody left their charger here, plugged into the wall, which is, has wires to whatever, the road, and then, the whole network of the city, the grid, they call it, right? I plug my phone in, now the electricity can travel into my phone, right? So electricity needs a path. When you have an aqueous solution, the ions are dissociated or broken apart or free, and it can provide a path for current. So you can say free. If you want to be fancy, you can say mobilized. Okay. So we're going to use Lewis structures to represent ionic compounds. So and Lewis structures, remember, are valence electrons only. So we're not concerned about the inner electrons. So when you have an ionic substance, then its Lewis structure looks a little bit different from a covalent, okay? So we're going to use square brackets. We're going to show the charge, and then the electrons are transferred, which means that the valence ones, right? Which means that the anion will have gained them, and the metal will have lost them, so they don't have them anymore. This relates to the crisscross rule. So if you remember how to do that, that can actually kind of help you check your answer. Or if you hated the crisscross rule, this might help you actually see why we do that, okay? So we'll do a simple one first, lithium fluoride. We did already discuss that lithium is +1, fluorine's -1. So what I'll do is for lithium fluoride, I'll write down, I'll do the Lewis structure, but also write like general ideas about them. You need square brackets, stuff like that, okay? So lithium is, now you can decide. So if it helps you, you can think of, or look where lithium is. It's in the first column. It has 1 valence electron, so it's going to lose 1. Or maybe you want to think of it like its charge is +1. That's fine. It doesn't really matter. And then fluorine gains 1. Or again, you can think of it already with its charge. That's fine, okay? You don't even have to write that down if you're like, you know what, I'm just going to draw the structure. It's really up to you. So when you draw the Lewis structure, we're going to have lithium. It has lost its valence electron, right? It does not have any more that are going to react. Yes, it's got inner ones that are really close to the nucleus, but lithium has lost its valence electron. The convention is to put square brackets. Okay? And then the fluorine gains 1. So it doesn't really matter where you put it. You can put the fluorine here, or down here, or up here. I'm just going to put it here. But you want to show fluorine gaining 1, okay? So it has 7. And it actually doesn't matter. So if you draw it like this, sorry, that's supposed to be, or like this, all of these are the same. The reason I draw it like this, because sometimes students, it's easier for them to see or for them to imagine that this electron or the electron from lithium would go closest to it. But it's, again, it's not like lithium ions look like Li, right? We've just used that as a symbol. So what I'm going to do, I'm going to put the one that's gained as an X. But you don't need to do that. You need to show fluorine with 8, but you don't have to show it as a different color. Okay, so metals lose. A couple things when you do this. So maybe you're going to be stressed out and you're going to forget the things that you already know. So let's say you've got lithium. You could look down here and it says metals. Maybe you remember that to the left of the staircase, we consider those to be metals, or they're going to be cations. Another thing too, and we'll talk about this when we get to Unit 2 in naming, but when you write the name of a compound, the element with the lower electronegativity has to go first. And you might say, well, how am I supposed to know the electronegativity? It's also on this table as well. So there's lots of ways you can kind of check your answer. And when you go to transfer electrons, this is the easiest because it's 1 and 1, right? Lithium has one valence electron. It's going to give it to fluorine. So if they're not the same, then you just keep adding elements till they get to losing the appropriate number and gaining the appropriate number to get to 8. So when you do ionic compounds, two things are different from when we are going to do covalent. So you have to have square brackets. And you have to have the correct ionic charge. So if this was -2, it would have to say -2, okay? It's not always 1. Okay? So let's do one that doesn't match up. So we'll do calcium and bromine. So calcium is in the second column, so it has to lose 2. Bromine is a halogen like fluorine, so it's going to gain 1. Okay, so calcium is going to lose 2. So if it helps you, what you can do is really lightly sort of draw them in, but then we're going to erase them. Okay, so if you have calcium and you need a bromine, so I'm going to do the same thing. I'm going to draw bromine 7 as dots. So then it takes, actually, let's do this. Even. It takes one of calcium's, bromine's charge is now -1. I'm even going to write -1 to emphasize the 1, but you don't have to. But is calcium satisfied? No. So we need another bromine. So what you shouldn't do is draw it over here, because then it sort of looks like the bromines are connected, which they're not, okay? Where you choose to draw the other bromine doesn't matter. You can put it here, you can put it up here, you can put it down here. Most people will just write it over here. But it doesn't matter, as long as you're sort of showing it connected to the calcium, okay? So draw in the 7. It has one spot for the calciums. Now calcium is good, 2 plus, or plus 2, I don't care. And the bromine is minus 1. So last year, and we're going to do this later, you guys did this ad nauseum, right? Crisscross. So the 2 goes down here, the 1 goes down here, and this is why. Calcium needs 2 bromines in order to lose both of its valence electrons. So if you liked that crisscross rule, then you can kind of use that to check your answer. If you didn't like it and you just want to think about this for now, totally fine. But you do need to be able to count how many valence electrons it has, okay, how many it has to gain or lose. So if you're having trouble with that, let me know. And you don't have to go through it like that. You can right away say, oh, I know calcium's plus 2, and then just make sure you have 2 bromines. You don't have to write them in and then erase them. You can go right to the final answer, okay? So magnesium iodide happens to be the same. I don't know why I picked this one, but. Again, these are similar elements. Magnesium is an alkali earth metal. Iodine is a halogen. You know what? This time I'm going to draw it with this. You just have to show that the iodine is, near the magnesium. It's not bonded to the other iodine. So ionic is pretty straightforward because it is the metal and the non-metal. There's not a lot of variety. It's plus minus. So as long as you can tell what the charge is going to be, then, or how many valence electrons there are, either way, then you should be good. Covalent, again, when you can now share, that's where things start to get a little bit gnarly. Okay, so we already did the classification of intra and inter. We are going to now mathematically identify the kind of bond that's formed because we're going to look at 2 types of covalent bonds. If your teacher called these compounds molecular, it's the same thing, okay? Molecular compounds have covalent bonds, so sometimes we just call them covalent compounds. Basically this time, no metals, only nonmetals. But again, there are some similar principles. When you have a compound, the lower electronegativity element is written first. So some of the rules are still the same, but not many. Okay, so in covalent bonds, we have nonmetals and sharing. So that is really the 2 main differences between ionic and covalent. And then there are some not lesser differences, but differences that aren't at the atomic structural level. They form molecules, not salts. They're not off. They can be brittle, but they don't have to be. There is a very wide range in the properties. So they could be solids, liquids, or gases. They do not make aqueous solutions because there's no ions, so they do not conduct electricity. But there are two subtypes. So when you have sharing, like I said, sharing is sort of, it's on a bit of a scale, right? Are you a good sharer? Are you a bad sharer? Are you greedy? Are you not greedy? So the same sort of thing occurs with atoms. So when you have a nonpolar, sometimes called pure covalent, but nonpolar covalent bond, that means equal sharing. And polar is unequal. And in grade 11, we will mathematically look at how you can figure out the difference. Hopefully by grade 12, you'll be able to look at the patterns more and you won't need the electronegativity values. But certainly in grade 11, you do not need to memorize them. You get that back of the periodic table every single time, okay? This has a big impact on how molecules behave with each other. So the fact that you have unequal or equal sharing differences means that you can get a bigger variety, right? So then when you have a certain type of sharing, then that's going to lead to the intermolecular forces. Whereas ionic, boring, plus, minus, plus, minus, plus, minus. No intermolecular forces, a very rigid repeating pattern. Okay, so what we're going to do is look at the different kinds of covalent bonds you can make. So when you draw the Lewis structures, they look very different from ionic. So the first step is deciding whether it's ionic or covalent. And usually, if you're given two atoms, that's what I'll say. Part A, mathematically determine the type of bond, okay? In the note, we'll do like what the structures look like first, and then we'll do how to subtract and figure it out. It's very straightforward, okay? So 2 electrons being shared is 1 covalent bond. So the first kind, so that's true whether it's nonpolar or polar. So you have, if it's nonpolar, then it's equal sharing of electrons. It can form between the same atoms, but it doesn't have to. But that is a common thing. So if your grade 10 teacher talked about diatomic molecules, hydrogen, oxygen, that it's always O2. So one of the first things about covalent, unlike ionic, is that you can have 2 of the same element bonded together. So we'll do hydrogen gas, oxygen gas, and nitrogen gas. So each element is going to contribute an electron. So in grade 11, there's 2 ways that you can show these Lewis structures. In grade 12, because we're going to do 3D eventually, I sort of encourage you to use lines and not bubbles. But in grade 11, if the bubbles help you see where the bonds form, then make bubbles, okay? Again, when I draw the Lewis dot diagram for each of the elements, I'm going to draw the electrons in between so that you can join them together. That's not really what it looks like. It doesn't really matter where you draw the bonds at all, or the electrons at all. So hydrogen is here. It has one valence electron. So then a covalent bond is the sharing of those electrons. Sometimes the electrons spend time around the one hydrogen nucleus, and then sometimes they spend it around the other one. So you can draw it like that, or like this. You can draw lines instead of bonds. It's the same thing. Each line or each bubble represents a pair of electrons being shared. Oxygen. How many valence electrons does oxygen have? Yes. Good. 6. Again, I drew those in a particular spot on purpose, okay? Because I'm going to draw my bubbles. So here I'm going to make a bond, and here. So not only can you have one bond or a single bond, when you have covalent, you can actually have double. And you can't, that's unique. You can't do that on ionic. Double is rare, more rare. So the basic premise is still the same. We still want to get to 8. So what you have to do is think of the lines or think of the bubbles as a pair, which is 2. So count by 2s, okay? So at any point in time around this oxygen, 2, 4, 6, 8. Around this oxygen. Whoops. See, I drew too many. 2, 4, 6, 8. Okay? Hydrogen's weird. There's only 2, right? So using the word octet rule is okay. So sharing, not transferring. The elements have shared electrons. Nitrogen is even weirder, even less common, the type of bond that exists. How many valence electrons does nitrogen have? Yes, 5. Okay, I'm going to draw them again in a particular way to keep my picture nice. Okay, I'm going to draw 2 out here. 1, 2, 3. Sometimes one of the reasons that students prefer to do bubbles is so that you can basically fill up the spots, okay? So really, let's say you have argon, it doesn't matter. So they have 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So if you look at an element, this one only has 2 paired up. So how many bonds does it need to make? 1, 2, 3. You can relate that to the charge. Nitrogen would be -3. However, when you do covalent, there are no ions, right? So just be careful of that. But you can definitely go through and fill it up, okay? This one needs to be bonded. Oh, there we go. This one needs to be bonded. Oh, there we go. This one needs to be bonded. There we go. And now all of its extra ones are paired up, okay? So started with 2, pair, 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 or it's all filled. So you would never leave it like this. and be like, oh, I'm done. No, take a look. Oh, I gotta fill those up, right? They need to be pairs. So we call that a triple covalent bond. And that's as far as you can go. There's no quadruple. So in a way, even though it seems weird, you can't, it's not infinite in the number of possibilities, right? It's either 1, 2, or 3. That's it. So there are a collection of molecules that exist as diatomic where there always has to be 2. So again, depending on who or what your grade 9 and 10 teacher emphasized, they may have already talked to you about this, but it's really important to remember. And one of the reasons it's really important to remember is what we're going to do in Unit 2 is write reactions. So when you write reactions, let's say for combustion, and you need oxygen to burn something, then one of the reactants is going to be O2. So if you just write O, then it's not going to balance right, and then you're going to come to me and say, Miss Todd, I can't get this to balance, and it's so sad for me because then I have to say, yes, you made a mistake. Sit down and figure it out. You know, that's sad for me, okay? So we do need to remember the diatomic molecules. So again, if you like, you know, tricks or whatever to remember them, they go in order. So acetine is a halogen. However, it's a very rare halogen. So we often, you might even find that people don't consider it a halogen, okay? So we're going to do iodine, bromine, chlorine, fluorine, oxygen, nitrogen, hydrogen. I bring clay for our new home. Sometimes people say house. There's one, if you Google it, there's one about beer, but that one doesn't go in order. I like this one because it goes in order. So iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and then sneak over for hydrogen. If you had Miss Coolin, she probably would have talked about it as a hockey stick. She likes that analogy, that it kind of looks like an L-ish kind of. Whatever is going to make you remember, okay? Because what we're going to do next is write reactions and balance, etc. So we really need to have, especially oxygen for combustion. That's a common mistake, and it can be very frustrating. So definitely remember those. So these are diatomic, 2 elements bonded together. That makes a equal sharing molecule or nonpolar. But what about polar? The Lewis structures for polar compounds are almost identical. There's just one extra little thing, okay? So polar covalent is unequal sharing of electrons, and you have to have 2 different atoms, but you do the same basic principle. So hydrogen has 1, chlorine has 7. So again, I'm going to draw the 7 with the 1 closest to the hydrogen. It's up to you if you want to draw the chlorines different. It really doesn't matter. Like if you want to draw X's instead of dots, it doesn't matter. Okay, so whether you like bubbles or not. Okay, all full. But when you have two different atoms, you have to be careful. And what you're going to do is you're going to look at their electronegativity values, which you never need to memorize. It's on the back of your periodic table, okay? So hydrogen, somebody tell me what hydrogen's value is, please. Yeah, beautiful. Okay? Or 2.20, yeah. All right? So it's on the back down here. Is there anybody who doesn't know where it is? Because I need to come show you. Good? Never need to memorize it. It's going to look exactly like this. Then chlorines. What's chlorines? Good. Much higher. And I'll show you in a minute how much higher it has to be. So what happens is that this value, the larger value, means that chlorine is more greedy for electrons. So when we say it's more greedy, what happens is, when you share, right, they spend time around both. So the electrons spend time around hydrogen, but then they spend time around chlorine, and then they spend time around hydrogen, and then they spend time around chlorine, and chlorine, and chlorine, and they love it. Okay, and then what happens is you get this buildup of negativeness. Is it a perfect ion? No. But there is a difference in the charge. And we have to show that because it influences the kind of intermolecular forces, okay? And intermolecular forces are vital to life on Earth, okay? So we have to take that into account. So when you figure out that something is polar covalent, you have to add one extra thing to its Lewis structure, okay? So the chlorine atom has a higher or greater attraction for the shared pair of electrons because it has a higher electronegativity. Do you need to memorize electronegativity? No, okay? You just have to know how to look it up on that chart. So the chlorine part of the molecule, it's not perfectly plus minus because it's not ionic, it's not transferring. So we say it's slightly negative. So how do we show slightly negative? We use the Greek symbol sigma. So it's kind of like an incomplete 8, okay? And the shared pair of electrons spend most of their time away from hydrogen. So the hydrogen part of the molecule is slightly positive. And how do you figure that out? Straight up with just the electronegativities, okay? You don't have to guess. You just look at the chart, okay? So I'm going to go back to my Lewis structure over here for a second. So over here, you're going to have to do this first. You're going to have to do the subtracting first anyways. So you'll already have looked up the electronegativity, and then whichever one is higher is going to be slightly negative, and whichever one is lower will be slightly positive. So you don't need to draw this mess here, but at least add this in. If you're missing these and it's a polar covalent Lewis structure, you're going to lose marks. Okay, so let's do water. Well, it says water's the most famous polar covalent molecule. We're even going to call it later on the universal solvent or the universal substance to dissolve things in. Okay, so I chose water because it's got two different types of atoms that have a different number of valence electrons. So hydrogen has 1, oxygen has 6. So in this case, it tells you H2O, so it tells you how many hydrogens. But in case it doesn't, you do the same thing, just keep filling it up. So we need 1 here. And then oxygen still has this 1 by itself, so we need 1 there. So whether you like lines or bubbles, either of those is good. The one thing you can't do, you can't do this. Because now you're saying 2, 3, 4, 6, 8, 10, like there's too many, so you can't do that. Pick bubbles or pick lines. Don't do both, okay? So now it's telling you it's polar. I'll show you how to do the math in a second. Oxygen is 3.44. Okay, so hydrogen is lower, so put a plus sign beside both of them. You should do that. And again, it's sigma, it's not easy. So as long as I can tell you sort of tried to make an incomplete 8, that's okay. It doesn't, like if you look at the font, it's on your computer, the symbol, it's like perfectly like, no. Perfectly like, see, I can't even do it. So just make it the best sigma you can do. Okay, so for the next part, you definitely need your periodic table, okay? Because we're going to look at how to mathematically figure out what kind of bond there is. And like I said, usually I'm very specific. Part A, do the math. Part B, draw the structure. You know, like I'll tell you to figure out mathematically what it's going to be. I'm not a trickster. I don't want to be tricky. Okay, so you look at the elements, and all you have to do is calculate the difference, okay? There are electronegativity tables everywhere. There's one in your textbook. If you want to use the same one that you're always going to use on the test, then, you know, it's on your periodic table. It's literally going to be this. It's going to be exactly the same. This one, although oh yeah, on yours too. So it even kind of makes the metals, like the left of the staircase, even a little bit darker. So it even helps with that, which not all of them do. So all you're going to do is subtract. This means change or difference between this little symbol called delta, like we're going to do delta T, and maybe you've done that already in science. When you subtract, it's possible to get a negative number. You can just ignore the negative. So this is called, these lines are called absolute value bars, which might be, I forget if it's grade 11, it might even be grade 12 math. Okay, so basically, whatever it is, just ignore the negative. That touches your dark side, then always do the bigger one minus the smaller one, and then it won't be negative. Okay, so it really doesn't matter. This is really meant to be very straightforward. Okay, so what we're going to do is you find the difference and then you compare it to this chart. So again, that appears exactly like what's on your table. If you want, yours is yellow. Maybe you could, well, it's actually kind of bold on yours. Maybe it's okay. What we're looking for is the range here. So if you get 0 to 0.49, then it's going to be nonpolar. 0.5 to 1.69 is going to be polar. And then anything greater than 0.7 will be ionic. Ionic, generally speaking, is easiest to tell, right? Because it's a metal and a non-metal. But, like I said, it's going to say, do calculate, right? So you have to do the math. Also, if it says to state the bond type or whatever, and you just put covalent, that's not good enough. You have to say polar, or sorry, if you want full marks, polar or non-polar as well, okay? So sometimes students are like, well, Ms. Todd, what if it's 0.493 or something like that? So it is sort of a continuum, we call it. So let's say it's a test or a quiz, it'll be very obvious. I go through them very carefully to make sure it's not one of those ones that's right on the middle. Again, I'm not here to be a trickster, okay? I want to know, can you use this chart and figure it out, all right? Okay, so here's a zillions of examples. When you have two of the same element, even if their electronegativity was 1,000,000, if you did 1,000,000 minus 1,000,000, you would always get 0. So you don't even have to do any math really there. Again, because it's kind of a continuum, there's another thing you can do called percent ionic character. So the first row in this table is delta ENG. Is it all good? I fixed your box. Mine here is, I fixed yours. Is that what you're worried about? Is all good? Did I take out? Oh. Because it's the same. I was trying to be faster. Okay, so percent ionic character is another thing you can do. Again, it's not like boom at 0.49, it turns into polar. It is kind of a continuum. So one of the things that as a scientist you might want to know is the percent ionic character. Maybe are there ions? Maybe is it going to be an electrolyte? So you can use that as a gradient as well. Usually we're just going to use the delta ENG line, okay? So then K minus F, and to be honest, once you do this a couple of times, like I don't even care, you don't even have to show your work. I'll try to sneak in my work here. So most of the time, students go in order that they're given it, and usually like I said, the lower electronegativity is written first, which means you're going to get a negative, which, maybe you don't like that. That's fine. You're just going to ignore it. So 3.16, what's that? It's ionic. For sure, right? Anything greater than 1.7. So now it does say there estimate. So you can go 3.16. 3.1 says it's 91. Maybe you want to write 91.5. Oh, Oh, why didn't I do these? These are 0. So then if it's 0, it's going to be nonpolar covalent. I'll even accept NPC, but maybe you don't like North Park. Me neither. I went to St. John's. That was like our rival. So. Usually we would do this over a couple of days. So the column at the end has the Lewis structure, and then if you look at the next page, there's like a summary chart for Lewis structures that we probably would do the next day. So what I'll do is I'll just sketch it in here, and then we'll go through the summary page as well, okay? I know it's tiny, just try to sneak it in. If you prefer one over the other and you're like, no, I'm just going to focus on the lines, no, I'm just going to do the bubbles, you don't need to write down both, okay? And again, something like this, maybe you're like, oh, that's obviously a metal and a non-metal, it's going to be ionic. But again, so then you can kind of check your answer, but you're going to get marks for doing the math, okay? So make sure you know how to do that. I know I'm totally in the way, sorry. Okay, so again, you're going to estimate the percent ionic character. So 2.16, you know, I don't know. I wrote 91.5, so maybe 67.5, 68. I'm going to be a rebel, put 68. Close enough, okay? We're not going to often use the percent ionic character. We're just going to use the delta ENG. Okay, so calcium chloride, it does say to draw the Lewis structure there. So this is similar to the ones that we did in the note. Calcium has to lose 2. And chlorine gains 1. Okay, so here's a good example. This is way too close, okay? There are so many other choices I could pick. I would never pick something this close. 1.78, yes, it's above 1.7, but that's pretty close, right? So that's very ruthless. So it's like 51.5 ionic. Yeah. Sorry, I wrote the bromine one. So for polar, you can just write polar. You can write PC. I would accept that. can have ones that are different elements and be nonpolar covalent. That's why it's so important to do the math, because you can't really tell the difference between them. H and Br is basically the same as chlorine. So bromine slightly negative and the hydrogen slightly. Okay, so the next sheet in your booklet should have the homework, but also this. So what we're going to do is, like I said, normally we would kind of do this the next day, but it is what it is, right? So we're going to do, if you look at the above the chart, it says mathematically determine the type of bond form, draw the Lewis structure, check that you have written ionic charges or partial charges if you require them. So that's exactly what the questions will look like. Do the math first. That'll help you decide what kind of Lewis structure to draw, and then check and make sure. If it's ionic, I have ionic charges. Polar covalent, I have the slightly positive and slightly negative. Okay? So basically we're going to do one of each. There's 3 spots, right? So calcium bromide. So do this part first. So you need to have what kind of bond and the delta E and G. If you get really good at this and you're like, I don't want to write down the subtracting, you don't need to, okay? Now, if you make a mistake, you don't write it down, then it can be difficult for me to tell where you did it. But so you decide, okay? So that's part A. Now that we have ionic, we know what kind of Lewis structure to draw. Okay, so you do have to decide, how am I going to figure this out? Do I think about how many calcium has, how many it needs to lose, how many bromine has, how many it needs to gain? Am I going to show the calcium ones, transfer them, erase them? What am I going to do? Okay? So calcium loses 2, bromine gains 1, so we need 2 bromines. Okay, and then C says to check for ionic charges. Do I have them? Yes, I sure do. Okay? Yes. No. You could do this and that would be enough. You can write -1, you don't have to write -1. But when it's 2, like that one, calcium +2 or 2 plus, you have to write the 2, okay? It's only the one that's understood. You know what? We'll take it back here. We'll do the... Okay, so this is a good one because silicon has 4 valence electrons, so this one can be tricky. So this is one where it doesn't tell you how many silicons, how many hydrogens, so just draw it and keep making the bubbles, okay? So first we should do the math. So 0.3 is NPC, nonpolar. Yes. Yes and no. When you're drawing it, let's say you draw the hydrogen first. That's fine. How many? So it has how many? Yeah, good. How many does silicon have? So what happens is when you do this, then you're like, here we go. But are we done? No. So yes, you can do that, but just make sure you fill them all in, okay? We need a pair here. It's like a little puzzle. Okay? That was a good question. And there are actually different ways to think about this. So in this case, when you're not given how many silicons, how many hydrogen, you can also look at how many valence electrons something has. So silicon has 4, it's going to have 4 bonds, hydrogen has 1. But then when you get to nitrogen and the ones that actually have like a charge, you do kind of have to be careful because it's more like nitrogen has 5, but it needs 3. So it kind of depends, whatever's going to make sense to you, okay? So now in part C it says to choose, do we need ionic charges? No, there's no ions. Do we need partial charges? Is this unequal sharing? No, nonpolar covalent, right? So then logically the last one we did ionic, nonpolar, we're going to do polar. Okay, so then let's do the same thing, sulfur and chlorine. Even the word polar often describes different ends, right? Like magnets, we say different poles, north-south. The Earth, North and South Pole, they're not the same. They don't have the same animals, etc. So when we're talking about polar, it's kind of like two ends to the molecule, a slightly positive and a slightly negative. So you don't need to memorize the electronegativity table, but again, you might find that there are patterns. So hopefully that's what we try to move towards in grade 12. So for example, when you see oxygen, fluorine, chlorine, they have a very high electronegativity. Their presence often will indicate, oh, it's going to be a polar molecule, okay? So this is another one too where you just kind of keep filling things up. So the sulfur has 6, chlorine needs 1. So wherever you start, it doesn't really matter. Just make sure they're all paired up. Chlorine has 7. When you do the subtracting, you might find it easy, like if you label your work, so then you don't have to go back and look at which one was lower and which one was higher, but it doesn't matter. Okay, that was intense. Great job. Tomorrow, I promise we have a tiny little bit to learn. Then we're going to do a lab, which is good. It's not going to make you cry or anything. It's not going to be super hard or anything like that. It's going to help with these concepts, and then you'll have a chance to do some work. So if you don't have a ton of time tonight, don't let that stress you out. If you work well in class tomorrow, and then Friday morning, you should be good, okay? Not that if you have time tonight, not that you shouldn't do some homework, but just to let you know. So the other side to this has the homework for it, some textbook questions, some worksheet questions. So I'm gonna put, as soon as I sit down, I'm gonna put solutions for the trends homework from the textbook, because the worksheet has them on the back, okay? Solutions for the ionic sheet the ionic part is separate from the covalent part of the worksheet, again, because usually we do it over 2 days. Then I'm going to put the solutions for both reviews, so the test review and the chapter review. Again, please remember, I hemmed and hawed. I put every single review question I would normally give on there. If it's too overwhelming, then, you take a look and decide what you can do, okay?